Previously, in the RH Saga, we never explained exactly what we mean by the word L function. Today, this will be rectified. Already 2 decades before Riemann introduced the Riemann hypothesis in 1859, another mathematician, Dirichlet, studied certain infinite series that he denoted by the letter L. These series behave in many ways like the Riemann zeta function. After Riemann, there was Dedekind, Ramanujan, Hecke, Artin, Maas, Langlands, and many other mathematicians who all discovered new examples, or even large worlds of new examples, of functions that all seem to behave very much like the Riemann zeta. Today, all of these functions are loosely referred to as L functions. They all encode some information about prime numbers. They all seem to satisfy the Riemann hypothesis, but no one has any idea how to prove that, even for a single L function. Today, we will focus on 4 properties that all these millions of examples seem to have in common. And sometimes you can prove that a certain L function has this or that property. Sometimes it seems to be the case based on numerical evidence. These 4 properties can be used as axioms to define precisely what we mean by the word L function. Keep in mind, though, that no one knows for certain what the ultimate best definition is of an L function. What we have is a rigorous but still a preliminary definition based on common patterns in all these examples. The 4 properties we shall discuss are analytic continuation, functional equation, Euler product, and temperedness. The Dirichlet series that defines any L function looks like this. A1 over 1 to the s plus A2 over 2 to the s plus A3 over 3 to the s, and so on. This can also be written as the sum of a n over n to the s over all n from 1 to infinity. In the L function examples we have seen, this series converges absolutely for s values in some right half plane of the complex plane. Absolute convergence means that even if you replace each term by its absolute value, the series is still convergent. When we say a continuation of the Dirichlet series, we mean a function defined in the entire complex plane that sort of continues the original function. The word analytic means the same thing as holomorphic, which means that the function has a derivative. It's a strange fact that when the function goes from complex numbers to complex numbers, having a derivative is equivalent to having derivatives of any order. So you can take the first derivative, the second derivative, the third derivative, and so on, of any analytic function. Since an L function may have poles, that means isolated points where the function values go off to infinity, we, strictly speaking, shouldn't call them analytic or holomorphic, but we should say meromorphic. But maybe a bit sloppily, we often just use the word analytic anyway. So, analytic continuation is something we will use as our first axiom. An L function can be extended to the entire complex plane, and it has derivatives of any order. Here is a plot of the Riemann zeta function as an ordinary function of a real input variable. You see a pole at s equals 1. For positive input, the function approaches 1, and for negative input, the function values are very close to 0. But if we rescale the vertical axis, you see the trivial zeros at -2, -4, -6, -8, and so on. The non-trivial zeros in the critical strip are invisible in this graph since the plot only shows real input values. Scaling back the vertical axis, we see that there is no obvious symmetry in this graph. However, some smart people realize that if you multiply the zeta function by pi to the power minus s over 2 times gamma of s over 2, then the graph looks like this. Now there is a perfect symmetry with respect to the line s equals 1/2. This symmetry is shown here for real numbers, but it extends to all complex numbers, so that if we define a new function, lambda of s, to be pi to the power minus s over 2 times gamma of s over 2 times Riemann zeta of s, then we have the functional equation lambda of s equals lambda of 1 minus s. For example, lambda of 5 equals lambda of 1 minus 5. So that's lambda of -4. We need a quick recap of the gamma function. Maybe you have seen before that the gamma function of 4 is 3 times 2 times 1. That's 6. The gamma function of 7 is 6 factorial, so 6 times 5 times 4 times 3 times 2 times 1, and so on. This is the rule for gamma of any positive integer. There is a natural extension of this to the entire complex plane, and you can find the definition, for example, on Wikipedia. For real input values, the graph of gamma looks like this. And here you can see, for example, that gamma of 4 indeed is 6, and that gamma of a non-positive integer is undefined. These are the poles of the gamma function. As a side comment, gamma values of rational numbers are incredibly interesting. For example, it is known that gamma of 1/2 is exactly the square root of pi. Back to Riemann zeta. We multiplied by this factor. It deserves a name of its own, and the standard name is gamma r, or gamma subscript r, of s. R is for the real numbers. To summarize, zeta of s has no obvious symmetries, but if we define lambda of s to be gamma r of s times zeta of s, then there is a beautiful symmetry, and we call this new function the completed zeta function, since we in some sense threw in a factor that was missing in order to achieve symmetry. A remark here, a little warning, is that sometimes we throw in a few more extra factors just to get rid of these ugly poles. And then we may use the letter psi instead of lambda for that version of the completed zeta function. For other L functions, it's a similar story. Here is the L function of k. No obvious symmetry. This time, I have to multiply by 4 to the power s over 2 times 2 times 2 pi to the power minus s times gamma of s. The resulting function has a beautiful symmetry, and just like before, the symmetry line is at s equals 1/2. Here, the number 4 plays a special role. It's an invariant of k called the conductor, and the rest of the factor also deserves a special name because it pops up again and again for many different L functions. We call it gamma subscript c of s, and c is for complex numbers. Here is the L function of a. Now I have to multiply again with 4 to the power s over 2, and also with gamma r of s plus 1, and the result is again beautifully symmetric. One way to guess that we should use gamma r of s plus 1 as our gamma factor is to compare the trivial zeros of the L function with the poles of the gamma factor. These two have to match up perfectly, and in this case, at the negative odd integers. Finally, let's do the L function of E. Now, the conductor is 14. And maybe you remember that the bad primes for this equation were 2 and 7. And I can again use gamma c of s to get a perfect symmetry. But this time, the symmetry line is at s equals 1. We could shift the L function of E, just move the entire graph 0.5 units to the left to get a uniform picture where the symmetry line is always at 1/2. This choice is called analytic normalization. Has nothing to do with analytic continuation. And if we do that, we must also shift the gamma factor so that it becomes gamma of s plus 1/2. Let's go to the LMFDB, find this curve, our favorite elliptic curve. Let's see. Go to the L function, and here on top we can choose normalization between arithmetic, that's the original, and then the gamma factor is gamma c of s, or we can choose analytic normalization, and then the gamma factor is gamma c of s plus 1/2. I should say one more thing. In our examples so far, we always had a reflection symmetry with respect to a line. For other L functions, we may get a rotational symmetry with respect to a point, or sometimes a similar but slightly more complicated symmetry. Anyway, the functional equation that the completed L function has a perfect symmetry, that will be our second axiom. Look at this sequence. 1, 3, 4, 7, 6, 12, 8, 15, 13, 18, 12, and so on. What is the pattern. I will say first where this sequence comes from. If you, for each positive integer, write down the divisors and take their sum, you get 1, 3, 4, 7, 6, 12, 8, and so on. This is our sequence. In fact, this has a name. It's the sigma function, also called the sum of divisors function. Now, let's try to forget that we know the definition of the sequence. Look at the sequence again. Is there a way to analyze and understand the pattern? Here is a general method that works for many sequences from number theory. The idea is to first look at the primes, then the prime powers, and finally all the other numbers. For the prime 2, the number is 3. For the prime 3, the number is 4. For the prime 5, the number is 6, and for the prime 7, the number is 8, and so on. In general, sigma of p is p plus 1. Now, for the next step, we work locally. And this means that we look at the prime powers for a single prime at a time. First, powers of 2. That's 1, 2, 4, 8, 16, and so on. The numbers here are 1, 3, 7, 15, 31. You can express this in different ways, but the rule is to double and add 1. Next, powers of 3. That's 1, 3, 9, 27. The numbers are 1, 4, 13, 40. Think about it. The rule in this case is to triple and then add 1. For powers of 5, maybe you can already guess the rule. Look at 1, 5, 25. The numbers are 1, 6, 31. The rule for going from one number to the next is to multiply by 5 and add 1. So for a sequence of prime powers, in general, we should multiply by the prime p and add 1. So that's a rule for the primes and a rule for the prime powers. Third step, all the other numbers. For 12, for example, 12 is 3 times 4. And the number for 12 is 4 times 7, which is 28. For 15, 15 is 3 times 5, we can take 4 times 6 to get 24. The general rule is to factorize into prime powers and then multiply the corresponding numbers. These 3 steps explain the entire pattern of the sigma function. Using them, you can reconstruct the prime values, the prime power values, and then the values for all the other numbers. Now, the point of the Euler product is that this method, these 3 steps, work for all L functions. Although the first step for the primes may be much harder, maybe even no obvious pattern. And the second step may be just a little harder than what we did here, but not that bad. The third step always works, just as in our example. The method we explained here can be translated into more abstract language. The sequence, like any sequence, has a Dirichlet series. In this case, it's 1 plus 3 over 2 to the s plus 4 over 3 to the s plus 7 over 4 to the s, and so on. And that the method, the 3 steps, actually worked is equivalent to the fact that the Dirichlet series can be factorized into an infinite product with one factor for each prime. And this infinite product is what's usually called the Euler product. I will try to show how the Euler product works for the sigma function. And then it's the same principle for all L functions. This is going to look much more complicated than it actually is. But hopefully it's helpful. So the plan is to explain the Euler product and expand it and hopefully get back to this same Dirichlet series. For the sigma function, each prime has a so-called local polynomial, fp of t. And they are all of the same form, namely 1 minus t times 1 minus pt. For example, f3 of t would be 1 minus t times 1 minus 3t, which is 1 minus 4t plus 3t squared. The Euler factor is, by definition, fp of t to the power minus 1. In other words, 1 over fp of t, which, for the sigma function, is 1 over 1 minus t times 1 minus p times t. Here, t is just a symbol for p to the power minus s. In other words, 1 over p to the s. This will be used later in the computation. I will also use computations of the form 4 over 3 to the s times 5 over 2 to the s equals 20 over 6 to the s. And finally, I will be using geometric series. For example, 1 over 1 minus 3t equals 1 plus 3t plus 3 squared t squared plus 3 cubed t cubed, and so on. Okay, let's do it. The Euler product. And the goal is, remember, to get to this Dirichlet series. So the Euler factor, we said, was 1 over 1 minus t times 1 minus pt. And the Euler product is the product over all primes of this factor. So that's 1 over 1 minus t times 1 minus 2t times 1 over 1 minus t times 1 minus 3t times 1 over 1 minus t times 1 minus 5t. And this Euler product continues forever, but for us it will be enough to use these 3 factors for p equals 2, p equals 3, and p equals 5. Now I expand each of the 6 geometric series here to get 1 plus t square and so on, times 1 plus 2t plus 4t square and so on, times 1 plus t square again and so on. And now I know that I won't need that many terms. So I'll just keep 1 plus 3t, and then it's 1 plus t and so on, and in the last one it's 1 plus 5t. And maybe you say there are 3 identical brackets here, but that's not the case, because the first one has t equals 2 to the minus s. In the second one, t means 3 to the minus s, and in the last one, t means 5 to the minus s. So now we substitute p to the minus s for t in each of the 6 brackets. We get 1 plus 1 over 2 to the s plus 1 over 4 to the s and so on, times 1 plus 2 times 1 over 2 to the s plus 4 times 1 over 4 to the s. Then it's 1 plus 1 over 3 to the s and so on, 1 plus 3 times 1 over 3 to the s, 1 plus 1 over 5 to the s, and 1 plus 5 times 1 over 5 to the s. Now it's a matter of expanding the brackets and collecting terms. I can multiply all the 1's. That gives me a 1. Then we'll look at terms with denominator 2 to the s. I get 1 term from here, and then I get a 2 from here. And just to be clear, I'm taking this term and multiplying it with all the 1's from the other brackets. And the 2 down here comes from the 2 up here. Over 3 to the s, I get a 1 plus a 3. Over 4 to the s, I get 1 plus 4 plus 2. Over 5 to the s, I have 1 plus 5. And over 6 to the s, I have 1 plus 3 plus 2 plus 6. And now you probably recognize the numerators. For example, the last one, 1 plus 3 plus 2 plus 6, that's the sum of the divisors of 6. So finally, we get 1 plus 3 over 2 to the s plus 4 over 3 to the s plus 7 over 4 to the s plus 6 over 5 to the s. And this is the Dirichlet series we wanted to compute. So all of this illustrates the principle of the Euler product, that the Dirichlet series can be factored into an infinite product with one factor for each prime number. And for any L function that such an Euler product exists, that will be our third axiom. Let's just go to the LMFDB again, to our elliptic curve E. Here you can scroll down to see a list of the first few local polynomials for this specific L function. You see the bad primes, they have simple local polynomials, and for the good primes, it's always degree 2 polynomials. But they are not all of the same form like they were for our example of the sigma function. A small side remark here, when the good primes has polynomials of degree 2, we say that the entire L function has degree 2. The final axiom, called temperedness, gives certain bounds on different quantities attached to an L function. To convey the idea, recall that we have seen the gamma factors, gamma r of s, gamma r of s plus 1, gamma c of s, and gamma c of s plus 1/2. Recall also that we have seen an example of Euler factors of the form 1 divided by the local polynomial, which factors as 1 minus t times 1 minus pt. Temperedness says two completely separate things. First, a precise rule for which kinds of gamma factors can occur, and second, a rule for what kinds of factors you get when you factorize an individual local polynomial. To summarize, we have described 4 axioms for what an L function is. Historically, the first person to formulate such axioms was the Norwegian mathematician Atle Selberg, around 1989. And those axioms define what's called the Selberg class of L functions, used in lots and lots of research articles since then. Today, there is a better, more precise version of the Selberg axioms, formulated in this paper by David Farmer, Ameya Pitale, Nathan Ryan, and Ralph Schmidt. Let's just have a brief look at their paper, because this is where you can find a complete and rigorous version of everything we have discussed today. In the abstract, they introduce these 2 main ideas that L functions can be viewed axiomatically, like we did today, or you can say that by definition an L function is something that comes from an automorphic representation. And they say conjecturally these 2 approaches to L functions are the same. But that is not clear at all with our current level of knowledge. In the table of contents, you see some of the words we have used previously, like automorphic L functions and L functions of motives, so motivic L functions. I want to highlight the section where our 4 axioms are presented in full detail, and that is section 2.1. Here is the full version of the definition we tried to convey today. Axiom 1, L of S is given by a Dirichlet series of the form sum of an over n to the s, where an is a complex number. This series converges absolutely in some right half plane, and it has an analytic continuation. Axiom 2, functional equation. There is a positive integer n, called the conductor of the L function, a positive integer d, called the degree of the L function, and then there are some other details here about the spectral parameters and the signature. But all in all, when you have the L function L of S, you can multiply by some gamma r factors and some gamma c factors, and also this additional factor, which is the conductor to the power s over 2. This completed L function has asserted boundedness property that we didn't discuss, but the main point here is the functional equation, saying that there is a sign epsilon such that lambda of s is this epsilon times lambda of 1 minus s. And the bar on top of lambda is complex conjugation, which you have to include if your A1, A2, A3, A4 coefficients are not real. Axiom 3, Euler product. There is a product formula, so L of S is an infinite product over all primes of a local polynomial evaluated at p to the minus s, all of that raised to the power minus 1. This is exactly what we did. Fp is a polynomial, and this polynomial has the same degree for all good primes. For bad primes, it has a lower degree. Finally, temperedness. The gamma factors had gamma r of s or gamma r of s plus 1, and those two gamma factors are specified here. These are the shifts allowed in the gamma r factors. For gamma c, we saw this plus 1/2, and this is specified here that 1/2 is permitted. Finally, point 2 of temperedness. If you factorize the local polynomial, then there's a rule for what kind of factors you may have. We had 1 minus t and 1 minus pt in our example. Here there are some specific rules for L functions. Finally, there is an axiom number 5 in this paper, and this illustrates the point that there is no universally agreed upon list of axioms that we know is the ultimate best definition. You can introduce the central character as an axiom. Personally, I prefer to think of it as an operation on L functions, and operations on L functions, that is the topic for next time.